having a great day. Happy Thursday. I hope that you're having a great day, and I hope that this doesn't change that. I'm going to leave the pens vertical while they kind of get things back to the belt. I tried to print out the review sheet for you guys for next Thursday's exam. There's no exam Monday, recall the syllabus. You have one exam remaining, and it's your final exam on Thursday. I tried to print out the study guide, but they've rekeyed all of the doors in this building, and the only one I currently have a key to is this room in my office. So maybe over one of our breaks, I can print out the study guide. If not, for sure you'll have it on Monday. It's ready, I just can't photocopy it yet. Yes, ma'am.
Will you be lecturing on Wednesday?
I will. So I'd like to get you the study guide this weekend so that you can start studying, but I can't promise unless someone can let me into the photocopy.
Can you just post it on D2L?
I could also post it to D2L. You guys all have the ability to open a PDF file. I could do that. So it's has a much higher likelihood of occurring if someone reminds me. But I'm certainly capable of that. Whether I'm capable of remembering is the next pressing question. Other questions? You guys hanging in there? 1 week to go. That was very enthusiastic. All right. So, I wanted to talk about atomic spectra today, the photoelectric effects some more. Atomic spectra, photoelectric effect. I want to use that as kind of a lead-in to quantum mechanics, although I may shift the order a little bit. And I may come back to that on Monday or later today, depending on how things go. And begin to talk about nuclear and atomic physics. So that's kind of a rough sketch of where we're heading today. Are there any questions about things that we've done lately, things that throughout the course have left lingering questions, comments, concerns? No? Okay.
Maybe, I can ask after class, quantization.
Quantization.
Quantization, I didn't really.
I'm going to go into that some more today.
Okay.
But the basic idea of quantization is that on some level the universe is going. So we often think of the universe as being continuous, but in some fashion it really is, in fact, kind of discretized, grainy, such that values come in step sizes, particularly when we start talking about energies. or things like charge, you can't pick any value you want. In some macroscopic sense, the universe is fairly continuous, but on fine enough levels, or if we're only talking about the sub-microscopic world, the universe really is actually very discretized. The step size, like when we were talking about charge yesterday, is quantized, meaning that you can't pick any value you want. You can pick from a list of values. Does that kind of work for you guys? Questions, comments, concerns? So, then picking up from yesterday, one of the concerns that I mentioned that kind of necessitated quantum mechanics was this idea of the ultraviolet catastrophe. Which was, if you plot intensity or brightness as a function of frequency or wavelength, experimentally that's what you observe. But theoretically, what you expected was something like this. So this is a problem of classical physics. The theory didn't match the experiment. And if you remember all the way back to chapter 1, the idea was that science has to be testable. That's the thing that makes science, is that it is testable. There has to be a test for falseness. And here, if you make predictions with classical physics theory, it predicts wrong. Wrongly, incorrectly. I don't know what the grammatically correct phrasing of that is. But it does not make correct predictions. And so when you test, it fails. That's a problem, right? And so there has to be some explanation for what's going on here. There's even, maybe a simpler problem that what this says is that as you go to shorter wavelengths, and which kinds of electromagnetic radiation have shorter wavelengths?
The radio wave.
The radio has really long wavelengths.
Ultraviolet.
So things like X-rays and gamma rays have very, very short wavelengths. The reason this is called the ultraviolet catastrophe is that for short wavelength things like ultraviolet, X-ray, gamma ray, what you're expecting is huge intensities, huge brightnesses. That implies more energy than is feasible. This does not coincide nicely with the idea of conservation of energy, right? Does that make sense? A moderately warm body here is emitting way more energy than it has a right to, than we can account for. At least according to classical physics. Thankfully, and probably based on our prior physics, obviously, it doesn't do that. It doesn't continue to increase its brightness as you go to shorter and shorter wavelength. Instead, it curtails and drops off back towards 0, so that you're actually winding up having very reasonable values for energy. But this was a problem for classical physics. remember, what's our working definition for temperature? It's the average translational kinetic energy per particle in a given sample, right? So the temperature of a given sample is, in some sense, a measure of its average translational kinetic energy per particle. Remember, that's just a measure of how much the particles are jostling about, right? Randomly moving back and forth. But those particles carry charge, right? And we were saying, I think yesterday or the day before, where does electromagnetic radiation come from? Well, it comes from accelerated charges. So classically, it shouldn't be that surprising that a warm body emits electromagnetic radiation. The problem comes from, classically it predicts it's giving off way more than we can account for in the short wavelengths. And thankfully that doesn't really happen. There were other problems. There's the atomic spectra. I'm going to pick on our simplest atom. What's our simplest atom? Hydrogen. What's hydrogen composed of? In its simplest sense, we could think of hydrogen as just a proton and an electron, right? So the other thing we said was that in our classical model, the electron orbits the proton and the hydrogen atom like so, just like a planet might orbit the sun. Hooray. But we said that electron was accelerated because the direction is changing, regardless of what the speed is doing, right? And so it should be emitting electromagnetic radiation. Is that all right? We're happy enough with that? Okay. So let me use this for this. We expect it's giving off electromagnetic radiation. When we look at the hydrogen spectrum, there are a couple of things that we naively might assume that we should get. We might expect that depending on how much this electron is accelerated, we should be able to get any color from the rainbow, right? Just, change the acceleration of the electron and you'll get different values of acceleration, consequently different values of electromagnetic radiation. That's all right? Another thing you might expect is, well, there's only one electron and maybe it has a fixed acceleration, and so maybe I only get one color of light emitted. Both of those, in a classical sense, you could probably make an argument for. That it should give off just one color, or it should give off all the colors. And here we have some hydrogen gas in a little partially evacuated tube. We're going to apply a strong voltage across it. It's actually about 5,000 volts with exposed electrical terminals, which is why we're doing this from afar. But you can see that it's giving off light. if we were to pass this through a prism, what we find is not that it's giving off just one color or that it's giving off all the colors. Instead, we get something like this, where there are several visible colors that it's giving off. And that is a problem for classical physics. The fact that it's giving some kind of barcode of frequencies of emission. In fact, if you look at this, if we were to replace the hydrogen with, let's go for helium. Definitely want to make sure this is unplugged before you play with it. You'll notice I have no issues using the Van de Graaff generator, but this thing I'm a little wary of.
Why?
It has exposed electrical connectors. It's capable of providing a lot more current than the Van de Graaff generator can. And consequently, it can do a lot more harm. So, I don't know if you remember what the hydrogen looked like, but for comparison's sake, here's the helium. Even my kind of defective colorblind eyes can see that that's a different overall color than the hydrogen's was. And what we find is that the helium has an entirely different set of spectral lines. And the thing that we take away from this is that the emitted light, the emitted frequencies of light, in some sense act like a set of fingerprints for a particular atom or element or isotope. I could put is we have some, I think, deuterium gas in there as well. This doesn't make sense classically either. Classically, you could make an argument for hydrogen only emitting one color because it only has one electron, and maybe there's a fixed acceleration, or you might be okay with it emitting all of the colors, but only being able to emit certain colors implies that, at least classically, there are only certain allowed accelerations for the electron, and that doesn't make sense because, remember, classically we're still very fond of this idea of Newton's second law. Newton's second law, what did Newton's second law tell me again? That the acceleration is proportional to the force that's applied to it and inversely proportional to the mass of the electron. Right? And so that would seem to say that if I vary the force, that I should be able to vary the acceleration continuously, right? I should be able to pick a specific force and get a specific acceleration in turn. But that's not what we're seeing. What we're seeing is that there are very specific emissions, which at least classically tells me that I have very specific acceleration, which is an oddity that wasn't understood at all. And then the one that I left off with was the photoelectric effect. And so I didn't really that's generous. I did a very poor job of describing this yesterday in the last 2 or 3 minutes of class. So let's try and do a more thorough job. So the photoelectric effect involves metals, and why did we need to use metals again? Some of the electrons in a metal are loosely bound, meaning that they're attracted to all of the positive nuclei, but at least some of them aren't bound to anyone in particular. Does that make sense? I take my, I'm sure you guys are counting the number of days until you don't have to hear analogies involving my dogs anymore. And for those of you counting at home, it's today plus 3 more lecture days plus the final. But I take my dog to the pet store. Only one of them, because only one of them is at all even remotely good enough to be allowed into public spaces. But I take Buster to the pet store, and I let him pick out his own treats. And so Buster wanders down the treat aisle, and he goes to each. He can't pick. He just wanders down the aisle and eventually, has sniffed everything. In some sense, the electrons in a metal are in a similar boat. Some of the electrons, so there's, in some sense, this sea of positive ions, or positive nuclei, I don't want to call them ions. And then there's at least one electron per atom, which is only loosely bound to the metal, because it's not just attracted to this proton or this positive nucleus, it's attracted to all of them. And so it can wander around through the bulk of the metal, through the body of the metal, and redistribute the electrons however it wants to. Does that make sense to you guys? So at least some of these electrons are loosely bound and are free to move around the metal. But because they're only loosely bound, when we talk about binding in physics, what we're really talking about is an energy debt. So these electrons owe just a little bit of energy to the metal. That's the thing that's holding them in place. And so if we shine a light onto this metal, well, classically, you might expect that the metal absorbs the energy from the light and can eventually kick out an electron. Does that make sense to you? We're happy enough with that? Yes, no, maybe so? So the electron is loosely bound to the metal. It only takes a little bit of energy to free it, and we can get that energy from light. At least at first order, qualitatively, what you expect happens often happens. You get light coming in and electrons coming out. It's only when you start to try and examine this more rigorously and perhaps a little bit more quantitatively. Do you guys know what I mean when I say quantitatively? So when I say qualitatively, I just mean kind of describe what happened. When I start talking about quantitative discussions, I mean, you know, use numbers, describe things mathematically. When you start doing that in the photoelectric effect, something weird happens. And the following is maybe a brief So in our wave model, if I have two red light sources, one is bright and one is dim, what's different about them? So,
Different wavelength?
so
I'm guessing.
that's, so
Clearly.
you have about a 33% chance of this. What are the three things that we could use to describe a wave in general? So frequency, amplitude, and wavelength, right? In truth, probably we only need two of those, but that's fine. So red light, for all red light, what do they have in common? What are the two things they share in common? Frequency and wavelength are the same in red light, all red light. Blue light has a different frequency than red light, but all blue light, for our purposes, there are different shades of blue, right? So we can, be a little more picky than I'm being at the moment, but all blue light has the same frequency as all other blue light. It has the same wavelength as all other blue light. Again, ignoring this idea of different shades. So how does a bright red light differ from a dim red light? Just the amplitude. And so I tried to draw that here, right? I tried to keep the wavelength the same and just change how tall the wave is. So classically, photoelectric effect, we'll look at classical, and we'll look at experiment. If we were to look at the effects of amplitude, of brightness, what do I expect? Which one carries more energy, the dim light or the bright light? The bright light absolutely carries more energy than the dim light.
Well, when we did the lab yesterday, most of them were the same.
No, they weren't.
No?
So you're over here.
Right.
What you were looking at was not the energy of the light. You were looking at the energy of a particle of light. But that's
Separate.
That's going to have to be the thing we're going to use to explain the experiment. But you can think about this just in terms of your common experience. If you put your hand next to a bright light, your hand starts to feel warm, right? If you put your hand next to a dim light, you probably can't tell. There's definitely more energy in the bright light than the dim light. there's definitely something else going on, which is why the classical explanation isn't going to agree with the experiment, and that's where what you're talking about is going to come into play. So, the effects of brightness classically, if the bright light carries more energy than the dim light, what do I expect in terms of how long it takes before I can kick out an electron?
Shorter.
Yeah, so effects of brightness, classically I would expect the bright light ejects an electron before the dim light. Is that alright? Because all we're really thinking of in this sense is that the bright light is carrying energy in, giving energy to all of the electrons, and eventually is going to give enough energy to the electron that it can free an electron. When we do this experiment, though, what we find is there's no difference, no observable difference in how long it takes to eject electrons, whether it's a bright light or a dim light. And moreover, as far as they can observe, there is, not only is there no difference in how long it takes, there is almost no delay. There's no measurable delay. The electrons get kicked out instantly, as far as their experiment can detect. Is that okay? Weird, but is it at least, is what we're saying understood? If the reasons aren't, that's okay. But the difference between what you expect and what you observe, does that work for you, at least? So, again, remember that this whole idea of physics is that it's a set of models that helps you make predictions about future events or allows you to, bless you, or allows you to analyze past events. Well, here's a problem for classical physics. It's not describing, it's not predicting what we observe. There's other problems too. If we look at the maximum kinetic energy, it should depend on brightness. What's that? But again, when we actually perform this experiment, what we see is that the max kinetic energy of electrons is independent of brightness. By the way, without turning this into too difficult an operation, the way that we're going to figure out what the maximum kinetic energy of these electrons is kind of a novel idea. If I take this golf ball and I throw it up in the air, it leaves my hand with what kind of energy? Kinetic. And what does it trade that kinetic for? Again, I like to think of energy like currency, so you trade one thing for another. Throw this up in the air. After it leaves my hand, the instant it leaves my hand, it has kinetic energy. And then it's trading what for what?
Potential energy.
It's trading kinetic energy for potential energy, right? It's losing kinetic energy. How do I know it's losing kinetic energy?
Potential energy is getting higher.
What observationally tells me, so you're right, the potential energy is getting greater, but what tells me that, how do I know I'm losing kinetic energy at the same time I'm gaining potential energy? What's happening to it? I heard the answer, I'm just told. It's slow, right? So after it leaves my hand, it starts slowing down. It's losing kinetic energy, but gaining potential energy. We're going to do the same thing for the electron, where we're going to fire it at, so we might be able to come up with a way of seeing how much kinetic energy we can impart to this golf ball, right? We might put like a series of shells or hoops and see, you know, what's the highest shelf or hoop I can get the ball into. Yeah? What I'm really doing there is I know what the potential energy of the various shelves are, and by looking at which one I can make it reach, I know how much kinetic energy I had at the beginning to give away. Does that make sense? And so different ones of us could probably get to different height shelves. We're going to do the same thing with this electron, where we're going to basically start to make some plate over here a little more negatively charged, and we're just going to keep ramping it up until this electron can't actually hit the plate anymore, right?
Is it like jumping the rings? Like the barrier, so it goes from one ring to the next, like it jumps out? Kind of.
It's a related idea. So we're looking at how much energy it has, and we're basically making it harder and harder to make it to the next stable spot, right? And so we're making it harder for the electron to make it up to here by making this a little more repulsive. And so at some point we get to we've made this so negative that this electron doesn't have enough kinetic energy to make it all the way to the plate. Does that work? And so from that we can measure how much kinetic energy it had at maximum, right? We can't tell the ones that, you know, not all of the electrons have the maximum kinetic energy. But what this will let us do is it'll sort out what the maximum kinetic energy was for the electrons that are being bombarded by this light. Hooray? Then, again, it doesn't care about brightness. And perhaps the weirdest thing in all of this is that classically we expect that it depends on brightness, but classically we don't think it cares at all about the frequency of the light. So it should be just going to say photo ejection. Should be independent of the frequency of the light. However, when you actually perform this experiment, what you find is that the kinetic energy is frequency dependent. In fact, I should not be lazy, I shouldn't say kinetic energy, I should say the maximum kinetic energy. By the way, do you guys qualitatively see why not all of the electrons should have the same kinetic energy? Why I'm talking about maximum kinetic energy? The argument I want to make is that which electrons have the easiest time getting out when they get struck by the light? The electrons at the top or the electrons in the middle or bottom? The ones at the top, why? Because they don't have to run past all of those protons, those nuclei that they're attracted to, right? They don't scatter as they travel, instead they're instantly gone. The ones that are struck down here and have to kind of burrow their way out of the metal lose energy along the way. And so the ones up here are going to exit with the most kinetic energy, the ones down here are going to exit with less kinetic energy because they gave some of their energy in crawling out of the metal first. Hooray? So that's why I need to be careful when we talk about maximum kinetic energies, because not all of the electrons in this experiment have the same energy. It's the maximum kinetic energies that we want to compare. The other weird thing here, which was totally unexpected, was that there exists a cutoff frequency for a given metal below which no electrons are ejected. And that doesn't care how bright the light is. In fact, for some metals, red light doesn't have enough energy to free an electron, no matter how bright it is. No one does darkroom photography anymore, which is kind of, this makes this a little bit of an anachronism. Has anyone ever, I don't know, seen on TV or maybe as an art project you did some darkroom photography? But in a lot of dark rooms you're allowed to use red light depending on what kind of film you're using. No one uses film anymore. But the reason for this is that the red light doesn't possess, apparently, enough energy. And this was very bizarre. It was something, classical physics has gone 0 for 3 here. This is a problem. Classical physics also failed in our ultraviolet catastrophe. It's also failed in our description of these atomic spectra. And so an explanation needed to be had. And the explanation was actually proposed by Albert Einstein, who at the time was not working as a physicist. He had received his doctorate, but had not been a particularly remarkable grad student. If anything, he had kind of earned a reputation for not being a very good academic. I don't want to besmirch the man's name, but his professors didn't think very highly of him. He was smart, but they didn't view him as dedicated enough to be successful. And so he was actually working as a patent attorney, as a patents clerk, in Switzerland when he did some remarkable work. In 1905, he publishes 3 papers, any of which were worthy of a Nobel Prize. The one he's probably most famous for is special relativity, which we'll talk about next week. Special and general relativity are the things that made him an international celebrity and make it so that his name is still known. Brownian motion, a brilliant work. He describes, if you've ever looked through a microscope and seen something, seem to flit around in water like it was alive, and it's not, you're probably examining Brownian motion. Or if you've ever spent a lazy weekend day looking at your bedroom window, and maybe there's sunlight pouring in through the window, and maybe you see like little bits of dust just kind of floating in the sunlight, and it looks like they're kind of just wandering back and forth. That's Brownian motion. And that's not classically understood at all. Einstein's able to explain it in a way that satisfied all. The third paper that he published in 1905 is the explanation of the photoelectric effect. And while he's most famous for special and general relativity, those were perhaps a little too revolutionary, too much of a difference from classical physics. It was clear he'd earned a Nobel Prize. In fact, in his divorce settlement from Leva Merrick, his first wife, she was actually an amazing mathematician. The divorce settlement in their original, in their divorce, cedes the Nobel Prize money to his former wife and his 2 children before he'd even won it. It was very clear that he had earned the Nobel Prize. It just wasn't clear when he was going to get it. Relativity was kind of wild, and the Nobel Committee wanted to give him a Nobel Prize, but didn't want to give him a Nobel Prize for something that would later turn out to be incorrect. In physics, you don't win the Nobel Prize for a career's worth of work, you win the Nobel Prize for one individual piece of work. And so what they did is they gave him the Nobel Prize for the photoelectric effect, because very rapidly the photoelectric effect his explanation of it seemed to be true. And so Einstein's explanation of the photoelectric effect was quite elegant and quite simple. Einstein argued that light is simultaneously both a particle and a wave. Where it has properties that are both particle-like and wave-like. Maybe that's a better way of saying it. But depending on how you ask light the question, are you a particle or are you a wave, will influence the answer. If you ask light, are you a particle, and the way you test it is by having it interact with matter, light behaves like a particle. If you ask light, are you a wave, and the way you're asking it is by watching it travel, it behaves like a wave. So when light travels, light interacts with matter, it displays particle-like properties. From here, so in some sense, you know, this is a little bit of a cop-out. We don't quite understand this wave-particle duality. That's what we call this. And it's hard to accept because we like to put things in bins. We like to give things classifications. You're a wave or you're a particle. You're, you know, you're tall or you're short, or you're old or you're young. We like to put bins, or we like to put things in bins that give firm definitions. This wave-particle duality kind of undoes that, and it's difficult. It's difficult for physicists. If you ever really want to torment a physicist, ask him or her to describe this wave-particle duality, explain it to you. We can tell you what it does, but the why of it is not something that's so clear to us. In some sense, when you ask, like, are you a wave, the answer will be yes, depending on how you ask the question, or the answer will be no, depending on how you answer the question. Probably, light is something that, you know, has both properties. It's, you know, we want it to be in just one of these bins or the other, but realistically, it's probably something more complex than our theory understands. Is that confession all right? So Einstein goes further, and remember we were briefly ago talking about the explanation of the ultraviolet catastrophe, why this is what was going on. We came to talk about Planck, and Planck fixed this by saying that if you had, say, a hot metal and it was, you know, emitting light, it emits light like this because we quantized, yesterday, we quantized the motion of the particles. And even Planck didn't really believe this. He just noticed that it explained what he saw, or what had been seen. It was a revolutionary mind like Einstein who saw Planck's explanation and thought maybe it really was more than just a cute mathematical trick to get the right answer. Planck didn't really, you know, necessarily ascribe real physical meaning to this idea that the particles in a solid have to vibrate at a specific, have to move back and forth, have to oscillate at a specific frequency. He didn't like that idea, but he noticed that it gave the right answer. Einstein looked at Planck's work and said, maybe there's something really physical here. Maybe this isn't just a cute mathematical trick. Maybe it actually has physical meaning. And so what he did is he said, maybe light itself is a quantized thing. And so he said that the particle of light and this particle of light would be called photon by others. But Einstein's particle of light, which we're going to start referring to as a photon, Einstein said that the energy of a single particle of light in some cases just equal to h times f. In other words, the energy of a single particle of light is proportional to frequency. And the weird thing here is that frequency isn't a thing for particles. Frequency is a thing for what? Waves. So somehow, even when Einstein's talking about light being a particle, it still has this memory of light being a wave too. It's weird and we don't understand it, but it's okay. This value h is Planck's constant, and again, I don't care that you remember values. I have all sorts of weird numbers stuck in my head. I'm not asking you to do that. If you decide to go on and become physicists, eventually just through sheer practice, you'll get numbers stuck in your head too, or whatever field you guys wind up in. You'll get all sorts of odd facts stuck in your head. If you've ever watched The Wizard of Oz, The Wizard of Oz, Dorothy goes to see the wizard, and he's not, when she meets him, he's not special, right? He's an ordinary person. He's just been doing this for a really long time. I think sometimes teachers forget how difficult it was for us to learn this stuff the first time we learned it. It's not that, so many of you can be physicists if you want to be. If it looks easy when other people do it, it's probably not that it was always easy for them. It's probably that they've been doing it long enough that it's become easier. But all this says is that the energy of a single particle of light goes as h times f. In other words, frequency and energy for a single particle of light are proportional. You can kind of view light when it's interacting with matter just like rain. That particles are striking the surface, like raindrops striking the surface. What does it mean to be a bright light in terms of this photon model, this particle model? What does it mean to be dim? What does it mean to be bright in terms of the particle model instead of the wave model? In the wave model, it's simple. If you're talking about amplitude. By the way, if I was what's the difference between this guy and this guy? There are several, but has a higher frequency, a shorter wavelength, also has less amplitude, but so if I was looking at a particle of this light and a particle of this light, which one has more energy? This is to Polyava's earlier point. If I just look at a single particle, which one has more energy? This one does, right? Why? Has a higher frequency, right? The wave would have a higher frequency. The particle, we don't really talk about it as high frequency. What does it mean to be a bright light or a dim light in terms of this particle model? What's the difference between a bright light